such as oxygen, hydrogen, gold, and copper. Since all the atoms that constitute elements are composed of the same particles, what is it that makes the elements different from one another? It is at this point that the importance of the number of the protons inside the nucleus emerges. What makes elements different is the number of protons in their atoms. For example, there is 1 proton in the hydrogen atom, the lightest element, 8 in oxygen, and 79 in gold. It is only this difference in the number of protons that makes gold different from iron, and iron different from oxygen. Electrons are particles spinning and revolving around the nucleus of the atom. This rotation is realized ceaselessly and in perfect order on paths we call orbits. To make a comparison between the size of electrons and the size of the Earth, if we enlarge an atom as big as the Earth, the electron would be in the size of an apple. Dozens of electrons in a space far too small to be seen even under the most powerful microscope revolve around the nucleus in different orbits at the unbelievable speed of 1,000 kilometers a second. That speed is the equivalent of being able to go from Paris to Milan in the space of 1 second. There are certain forces that keep the atom, the fascinating structure of which we have been describing, together. In order to understand this, let us look at the center of the atom, the nucleus. At a carbon atom nucleus, for example, the atomic weight of a carbon atom is 6. This means there are 6 protons in the nucleus. Yet there is an interesting point here. All protons carry a positive electric charge, and particles with the same charge repel one another. How is it then that protons, which should repel one another, remain together? In the face of this question, scientists hypothesized that there was a force binding protons together, and named it the strong nuclear force. This strong nuclear force is one of the 3 basic forces operating in the atom. The second is the weak nuclear force that affects the neutrons alongside the protons. The third is the electromagnetic force, which keeps the electrons revolving around the nucleus of the atom in their orbit. Electrons carry a negative charge and are attracted by the electromagnetic force towards the positively charged nucleus. The centrifugal force they acquire as they revolve balances the electromagnetic force, and they thus remain in orbit. There is one more force operating in the universe as a whole, in addition to these 3 basic forces that affect the atom. That is the gravitational force. The information we have seen so far can be found in any book on physics, yet there is an important fact that is generally never mentioned. The strengths of these 4 fundamental forces in the universe are very different, and that difference depends on a very sensitive balance. The strong nuclear force, for example, is some billion times greater than that of gravitation. There is a more than million-fold difference between the strong nuclear force and the electromagnetic force. What would happen if these differences were slightly different? For instance, if the strong nuclear force in the atoms that comprise your body at this moment were slightly weaker, your body would instantly fragment. A variation of just 1 in 1,000 would be sufficient for this to happen. Yet thanks to the delicate equilibrium of the four fundamental forces, the atoms that make up your body and the rest of matter always remain stable. This sensitivity in the levels of the four fundamental forces astonished scientists. One of these, the renowned physicist Paul Davies, makes this comment: "Had nature opted for a slightly different set of numbers, the world would be a very different place. Probably we would not be here to see it. When one goes on to study cosmology, incredulity mounts. Recent discoveries about the primeval cosmos oblige us to accept that the expanding universe has been set up in its motion with a cooperation of astonishing precision." Another striking aspect of this fact emerges when the concepts employed are elaborated on. We have seen that scientists refer to the physical forces in the universe as the four fundamental forces. Yet that definition does not explain the existence of these forces and why they are so finely balanced. If we go beyond that definition, we encounter the fact that Almighty God orders the universe at every moment. This truth, arrived at by modern physics, is in fact nothing more than the discovery of a secret revealed in the Quran 1,400 years ago. God keeps a firm hold on the heavens and earth, preventing them from vanishing away. And if they vanished, no one could then keep hold of them. Certainly he is most forbearing, ever forgiving. At the outset, we said that the atom was the building block of everything we see around us, and we have indeed witnessed how the flawless balances in the atom are maintained with great sensitivity. In this section, we shall be taking a further step and examining how atoms combine to form molecules, another link in this chain of miracles. Molecules are the smallest units determining the chemical properties of matter. These small bodies are made up of 2 or more atoms, and some of thousands of groups of atoms. Atoms are held together inside molecules by chemical bonds, determined by the electromagnetic force of attraction. The arrangement of molecules in different combinations give rise to the diversity of matter we see around us. Carbon is the most vital element for living things, because all living organisms are constructed from compounds of carbon. Structures as diverse as the cell membrane, the bark of a tree, the lens of the eye, and the white of an egg are composed of carbon compounds. Carbon, combined with hydrogen, oxygen, and nitrogen in many different quantities and geometric arrangements, results in approximately 1.7 million compounds. One of the most significant properties of carbon is its ability to form chains very easily by lining carbon atoms up one after another. Some carbon compounds molecules consist of just a few atoms. Others contain thousands or even millions. Also, no other element is as versatile as carbon in forming molecules with such durability and stability. Carbon is unique among the elements in the number and variety of the compounds which it can form. Over 250,000 have already been isolated and described, but this gives a very imperfect idea of its powers, since it is the basis of all forms of living matter. Science today is still unable to fully understand the capacity of the